This video is a tutorial sheet on using sketches for compensator design. So it's summarised again here. We're going to give a few tutorial or exam style questions on sketching root loci and then using them for compensator design. The idea is that students should pause the video after reading the questions and attempt the questions themselves. Only have a look at the solutions provided here after you've had a proper go. So to re-emphasise, the tutorial questions here are focused on using a basic root locus sketch or root loci sketch for estimating compensator gain by hand, and this is useful because it gives us insight into roughly where the gain should be. Now, just a reminder of what we're doing. We've got simple feedback loops of this form here. We're going to write the compensator times the system GM as k n over d, where k has all the gain components and n over d all the dynamics. And we've shown in the previous video that if S is a desired and achievable being a keyword, closed loop pole, then you can find the compensator gain using this formula here, which is summarized as the product of the distances from S to the open loop poles divided by the product of the distances of S to the open loop zeros. Now the assumptions we're going to make, we're going to expect you to create a sketch, and we should emphasize this word here, a sketch for the root loci, and from this identify the desirable locations for the closed loop poles. So you're basically looking for an S which you believe to be on the root loci. In practice it will be close, but as long as you're close, that's good enough. And then you're going to use that sketch to estimate the value of k that will actually give us that specified closed loop pole. And finally, just because we're learning here, it might be useful to check you're working against MATLAB after the event. First question then. Control system is given by the following. You'll see we've got gk is k s plus 3 over s plus 1, s plus 2, s plus 4. And the question is, first sketch the root loci and then estimate the value of k such that the root loci cuts the imaginary axis, and what are the corresponding closed loop poles. And you've got a reminder here that the idea is that you're going to use estimates and approximate answers. You're not asked for an analytic solution, which will be difficult given you've got 4 poles here anyway. So now is the time to pause, and I will go on and give an indicative solution. So there's the system again. So the first step was to plot the root loci. So let's do that. I'm going to mark all the poles. We had a pole at 0, we had a pole at -1, we had a pole at -2, and we had a pole, I've put that in the wrong place, this happens, and we have a pole at -4. We also have a 0 at -3. So that was the first step. Next, we want to look at the asymptotes. Now I can compute the centroid as the sum of open loop poles minus the sum of open loop zeros. So that's -1, -2, -4, plus 3, all divided by 3 because the excess of poles over zeros is 3. And that gives you -4 over 3. There are 3 asymptotes, so the directions will be 180 degrees or plus or minus 60 degrees. So I can mark the asymptotes. Now you'll notice I've marked one of them for you here already because it's quite hard to sketch these accurately on a computer screen. So there's some of the 3 asymptotes for you, and there's the centroid marked. The next thing is to say, okay, which bits of the real axis are on the loci? So we need an odd number to the right, so that's those bits using this hashing. And finally, let's look at what the root loci might do in the area of interest, and we're looking at these poles closest to the imaginary axis. So these two will come together and go off something like this. So the question we're asked is, where does this root loci cut the imaginary axis? And what I'm going to do is I'm going to say approximately we cut the imaginary axis at 2j. Now I realise that is an approximation, but we've only done a sketch. So having got that, I can now use my formula to get k. So you remember that k was given by the norm of d divided by the norm of n. And I'm going to put in s equals 2j. So, what are we going to get? I'll write it in full this time, and then we might be quicker in future questions. So k is going to be 2j times 2j plus 1 times 2j plus 2 times 2j plus 4, all divided by 2j plus 3, and we've got to remember to put a norm around all of that. Now, I can use Pythagoras to solve this. So for the 2j, I just get 2, and now I'll use the square root for the rest because I'm going to do Pythagoras. So 2j plus 1 using Pythagoras gives me 5, that's 2 squared plus 1 squared. 2j plus 2 gives me 8, that's 2 squared plus 2 squared. And 2j plus 4 gives me 20, which is 2 squared plus 4 squared. And 2j plus 3 gives me 13. Now, that square root doesn't look particularly tidy, but remember we're doing approximation, and you can very quickly see that this is going to be roughly 15 without doing any exact computation. So the suggestion is that if you use k of 15, you should get your closed loop poles pretty close to these crossing points. So what I'm going to do is I'm going to use MATLAB to check and see, have I indeed got a sensible value of k that does what I asked. So here's the MATLAB window. So there's my transfer function. I've put it in, and now you'll see I've simply put this value of 15 into my pzmap command to see what I get. And there's your answer. You've got poles at 0.138 plus or minus 1.9i. Now it's not exactly on the imaginary axis, which isn't surprising because we've used estimates and approximations, but it's pretty close. And so what that's telling you is the value of 15 you've come up with is actually a good value for meeting the question that's asked. Now remember, with real systems, numbers are always approximate, probably to 10%, and so this k of 15 has told you what you want. It's in the right ballpark. Example 2. A control system is given as this: k of s, s plus 4, s squared plus 8s plus 32. And again, same as the previous question, it said estimate the value of k such that the root loci cuts the imaginary axis. And what are the corresponding closed loop poles? Now, question for you to do by yourself, I'm not going to give an answer, is what value of k would you choose and why? So, as before, we start by doing the root loci. So first let's mark all the roots. We've got a pole at 0, we've got a pole at -4, and what may not be obvious to you is we've also got poles at -4 plus or minus 4j from this quadratic factor, so I can mark those two poles, one up there and one down there, and no zeros. So next I want to do the asymptotes. Well, if I do the computation for the centroid, remember you do the sum of the open loop poles, which is -12, minus the sum of the open loop zeros, which is none, divided by 4, so you get -3. And because the excess is 4, you're going to get plus or minus 45 degrees, plus or minus 135 degrees. And you'll notice I've put the asymptotes on the graph for you already. And again, that's because trying to do this by hand on a screen, you just end up with a mess. So it was better to put them down. So there's your asymptotes. Next then, which bits of the real axis are on the loci? Well, we need an odd number to the right. So this is on the loci. But other than that, there is no other bits with an odd number to the right, so there's no other parts of the real axis which are on the loci. And finally, I need to do my sketch. So clearly, these two will go off like this. Now, I haven't done angles of arrival and departure, so you might say, well, it's not immediately obvious how they will leave, but I'm not going to worry too much about that. These two will come together, they will meet, and then they will go off like this. Okay? Now, we've been asked, where do the loci cross the imaginary axis? Somewhere around here, and I'm going to postulate that that's roughly 3j. Again, it's an estimate, and you have to understand it's an estimate because we're trying to get indicative values of k that give us a good start point before we do fine-tuning. So let's try and see if this works for us. So our formula, remember, is k equals the modulus of d over the modulus of n. In this case, the modulus of n is 1, so I've just got the modulus of d. So what have I got? First, I've got just s, that's 3. Then I've got s plus 4, so that's going to be 3 squared plus 4 squared. And then, this bit I'm going to do a little an aside, and a little balloon here, so you can see what I'm doing. So s squared plus 8s plus 32 is going to go. Now, if s is 3j, then s squared is minus 9, 8s is 24j, and then you get plus 32, or in other words, you end up with 23 plus 24j, and that's for this quadratic factor. So having done that, I now see that that's going to give me the square root 23 squared plus 24 squared. Now, this is going to give me 3 times 5 times 24 times root 2. And perhaps I should emphasize this is an approximate, and this gives me approximately 500. So remember, there's no point worrying about the decimal places. I've approximated 23 squared plus 24 squared by just root 2 times 24 squared or whatever, because the difference is not important given we're estimating anyway. Okay, let's move to MATLAB and see whether this k has indeed worked. So I enter my g, there it is, and then I find my closed loop poles, and you'll see I've put 500 into that command as expected. And what do you notice? I get pole positions minus 0.13 plus or minus 3.12i, so it's pretty close to where I expected, and therefore this k of 500 is in the right ballpark. So my crude hand design has actually been quite effective. Example 3. You've got a simple system here, and what you're asked to do now is use root-loci methods to estimate a gain which gives a good compromise between speed of response and input activity, and obviously settling time and other things of that nature. Alright, as ever, we're going to start by sketching the root-loci and seeing what we've got. So we've got a pole here at the origin, and we've got 2 poles at minus 1. If I calculate my centroid, then you'll see you're going to get minus 1 over 3, which is minus 2/3, and you'll have angles minus 180 degrees plus or minus 60 degrees. So I can mark my centroid, and again you'll see that I've done it for you to make sure the sketch is reasonable. Okay. Next, I can do real axis on the loci, so it needs to be an odd number to the right, so we've got this bit, and indeed, we've also got this bit. And then finally, I can add in a reasonable sketch. Now, because this one is going to the left, I know that where these two meet is certainly going to be to the right of minus a half, so I'm going to get them joining somewhere like this. Can't be over precise, but that's good enough. And the question was, give me a reasonable compromise between speed and input activity, etc., etc. So if next I draw my line of 45 degrees, so there's my 45 degree line, which gives me a damping. So I'm going to go for a damping of approximately 0.7, and that corresponds to that point there. And that is given, now you see I'm going to be very crude here, it's going to say roughly if s is minus 0.3 plus or minus 0.3j. So there's my estimate for the closed loop pole position, which will give me this compromise. So now I need to find the k. So you remember the k is given by modulus of d over modulus of n. In this particular case, the modulus of n equals 1. So I'm just going to get the modulus of g. So what I've got to do is substitute in that value of s. So k is going to be the square root So if I have just s, I get 0.3 squared plus 0.3 squared. And if I have s plus 1, then I'm going to have 0.7 squared plus 0.3 squared, and that particular term will be squared, because clearly there's two of them. Now, what does this give me? It gives me 0.3 times root 2 times, and then you're going to get 0.7 squared, which is 0.49, 0.3 squared, which is 0.09, so you're just going to get 0.58. Because there's a square on that factor, it comes out of the square root. Now if you put all those together, what you're going to get, I'm not going to get my calculator out, but you can, it's approximately a quarter. Let's keep numbers simple because we're doing estimation anyway. So there's my estimate of the k required. And again, as before, let's use MATLAB and see, has this worked? So there's my g, we enter that, and now let's put in a quarter and see what we get. And you see you've got poles minus 0.29 plus or minus 0.3 j. So in this particular case, my estimates have given me a very accurate answer. I've been quite fortunate with the choice I've made there. Final example. Determine the value of k which makes the slowest system closed-loop poles approximately real and equal. So we want the slowest poles to be approximately real and equal. So as before, let's start with our root loci. You'll see we've got a pole at -1, we've got a pole at -3, and we've got a pole at -5. If we look at the centroid of the asymptotes, you see you get -1, -3, -5 over 3, which is -3. And we have angles of -180 and plus or minus 60 degrees. So again, as before, you'll see the asymptote, or the key asymptote, has been marked there for you to save some effort. I can mark the bits of the axis which are on, so the bits of the loci on the real axis, using odd numbers to the right. There they are. And again, if I use the observation that this one is going to the left, then I know that where these two meet before they go off has got to be to the right of -1. Okay, because the net change in those two poles on the right has to be moving to the right, because this pole over here on the left is moving to the left. So I'm going to guess that this intercept point is approximately -1.8. Now that is a guess. Okay, you can calculate them exactly from breakaway point analysis, but it's quite numerically intensive, and it's really not worth the effort. If you really wanted that value, go to MATLAB. So I'm just guessing it's about -1.8. So that will make the slowest poles real and equal. So now let's find the corresponding k. So k is going to be the modulus of d over the modulus of n. Now, what I'm going to do is use a value, s equals -1.8. So what you're going to get is, if I just write d in full, s plus 1 is going to be -0.8. S plus 3 is going to be 1.2. And s plus 5 is going to be 3.2. So you'll see they're all real numbers, so I don't even need Pythagoras for this case. The answer comes out quite straightforwardly. Now what I can do is I can say that these two together are approximately 1 times 3, and the answer is going to be about 3. Again, I'm not worried about decimal places. You can do that if you really want. But I'm saying if you choose k to be about 3, you'll find you're roughly in the position where those two poles are real and equal. Again, let's go to MATLAB and see if that has worked. So enter my transfer function. There it is, and you'll see in this pzmap command with feedback I've put the value of 3, and what you get? You have a pole at -2 and a pole at -1.7. So they're not exactly real and equal, but again I think you would agree they're fairly close. This k has put you in the right ballpark, which is what you were asking for. So in conclusions, we've given a number of tutorial questions on compensator design using a root-loci sketch. And we should emphasize this design is an estimate, and you may need some fine-tuning, okay? But the point is, it's indicative of the required value and has given you useful insight. If the K that you've tried to apply is a long way away from this, you're probably way away from where you need to be. If you really do want precise answers, remember you're recommended to go and use appropriate software tools.